Thank you very much, Mr. Chairman. My name is Vittorio Di Cocco from CuZnAl University, Italy. And the work that I show you today is about a grain size influence on follicular propagation in a kind of shape memory alloy based on copper, characterized by a pseudoelastic effect. A few words about shape memory alloys. Shape memory alloys are a wide class of material characterized by a particular properties. The property to recover the initial shape also after high values of deformation. This is due to ability to change the initial structure, often named as austenite, to a final structure named as martensite. In this picture, we can see a schema of this transformation in the relation between the stress strain. In the first stage, we can see a typical elastic stage characterized by austenite-Young modulus. This structure is able to have many stresses up to sigma p values. This is a level of stress where the transformation from austenite to martensite takes place. The second stage is characterized by this transformation. Sometimes is schematized as a plateau, but in real results we have just a little bit slope. When all the transformation of austenite is performed to martensite, we have another stage, elastic stage, characterized by another Young modulus, because is another material. This transformation is reversible and allows to the material to recover the initial shape. Where is stored the initial shape if the structure is fully transformed? It's stored inside the grains, because this transformation takes place without a recrystallizations, without any recrystallization. It means that the boundary of grains seems to be the same, can change the shape, but no one atoms is able to migrate in other grains, and no other grains born during this transformation, reversible transformation. We have two different mechanical behavior. In the first one, the reverse transformation to get the initial shape can take place because the material haven't enough energy to recover its initial structure. But we can heating the material up to temperature greater than the critical temperature. In this case, the transformation inverts from martensite to austenite take place, recovering the initial shape. In the second case, we have a critical temperature of material less than the environment temperature. In this case, the heating is not necessary to recover the transformation, and the macro behavior seems to be like a fully elastic transformation, but the relationship between sigma and the epsilon is not linear. In this case, we talk about of pseudo-elastic transformation. This is the case of our material. The material produced in our laboratory is characterized by this chemical composition. We can see a 73% of copper, 21.80% of zinc, a high values of aluminum, 5.04%. Other elements are used to balance the chemical composition without cerium. These alloys I named in this work, these alloys as alloy A. And the second alloys is characterized by the same chemical composition, but in the balance elements we used 0.25% of cerium in order to obtain a refinement of grains. Here we summarized the analysis performed on this material in order to evaluate the structure properties and the mechanical properties, tensile properties. And then we performed a follicular propagation test in delta P constant conditions using just one stress ratio R equal to 0.1 in sinusoidal loading waveform at 30 Hz of frequencies. The temperature was the temperature of laboratory, but this material is a pseudoelastic material. In this case, it means that it is not necessary heating the material in order to have a recovery of initial shape. In this picture, I reported the shape of grains of alloy A and alloy B. You can see that the grains are equiaxial, but if you see the marker, you can see that the effect of cerium is very strong on this because the grain size is about an half. Using a Jeffrey methods, it's a methods used to evaluate the main grain size. We can see that the alloy A is characterized by very big grains, and alloy B, the grain size is quite an half of the grains of alloy A. And here we reported the values of plateau during loading conditions. So in terms of structure, here you can see the diffraction spectra. These are results of XRD analysis performed on the surface of tensile test. We can see in unloading conditions the presence of this peak in about 41 degrees. This is the angle 2 theta, the angles of diffraction. And these peaks disappear when the material is loaded at high values of deformation. It is due to changing of structure because the plane characterized by this peak of diffraction, it disappears. Here you can see this peak present in loading and loading condition. This peak is stable. We think this is the peaks corresponding to the habit plane, which is the plane where the transformation, direct and reverse, takes place. So, this is the first results in terms of the ADN delta K fracture propagation. We can see this strange relation characterized by different stages. In traditional material, metallic alloy, we sometimes saw 3 different stages. The first, the second, where the Paris law is adopted, and the third stage. Focusing on the second stage, we can see that in this case we have a sort of plateau characterized by a very low slope, which starts about 14 megapascal square meter and ranging over 15 megapascal square meter. The second stage is the second analysis performed on alloy B is this. We can see the presence of different stages like alloy A, but the values of delta K of stage 2 are less than the alloy A. This is due to the influence of grain size because the chemical composition seems to be quite similar, and the diffraction spectra between the alloy A and alloy B is practically the same. So the range of this stage is less than the width of stage 2 is less than the stage 2 of alloy A. In terms of fracture surface micromechanism, fracture mechanisms, we can see the presence of alloy A of 2 different fracture micromechanisms. In the first one, we have the presence of striation, ductile striation in intergranular propagation. And here we can see the cleavage often observed in intergranular propagation. In alloy B, you can see the different scale of the grain. We can see the same fracture propagation micromechanism. This is the striation. Here we can see the cleavage, which characterizes the fracture propagation in intergranular manner. So from the point of view, from this point of view, stage 2 of two alloys are very close. Trying to apply this simple relationship between, in order to evaluate the plasticity added to the crack tape when is applied a values of K1 of load, and trying to change some values like this, using sigma plateau instead of the sigma y, you can see to evaluate, you can try to evaluate the region characterized by a stress level greater than the epsilon plateau. In this case, this is the region where the reversible transformation from martensite to austenite can't take place, because the level of stress is always higher, considering K1 mean. The values adopted for sigma plateau are the same measured in tensile test, and we can try to relate these values to the main grain size. With this formula, we can evaluate the fraction of grain which are not interested by reverse transformation. In order to plot this curve in a traditional DRDN delta K diagram, we can use this relation in order to eliminate the K1 mean and put in a delta K. So this is the first results. In green, you can see the curve used to evaluate this, this region. And corresponding to the start of stage 2, we can see that the region where the structure can take the form of austenite is about 1 grain. At the end of this stage, the region seems to be bigger than this grain. Applying the same relation for the alloy B, characterized by smaller grain, you can see the same results. So this is the initial of stage 2, and in this point corresponds a fraction of unchanged structure big quite as 1 grain. So here I summarized the conclusions. We have 2 main conclusions. The first conclusion is in terms of metallurgical influence of cerium on the grain size of copper-based shape memory alloy. The content of the addition of cerium strongly reduces the grain size and strongly influence the mechanical behavior of this alloy. And the second one is the influence of changing of structure in terms of fatigue crack propagation, which in this kind of material seems to be characterized by over of 3 stages, the stages usually observed in traditional metallic alloy. Thank you very much.